So today we're going to talk about the types of solids. There are four. The first type of solid is an ionic solid. Go ahead and write that down. Ionic solids have these crystal structures where the negative ion is attached to the positive, to negative, to positive, to negative, to positive, over and over until they form this organized crystal structure. Because of this strong crystal structure, they have high melting and boiling points. The crystal structure holds the ions in place, so as long as it's in the solid form, it cannot conduct electricity. So solid ionic compounds do not conduct electricity. But if you melt it or dissolve it, then the ions are free to move because you've broken that crystal structure and it will conduct electricity. So solid does not, but liquid, sometimes they call it molten, liquid or aqueous, will conduct electricity. Okay, now yesterday you were supposed to watch the video about solutions and making solutions, and I said that like solvents dissolve like substances. So ionic compounds are very polar because they have the positive and negative ions, so they're extremely polar. So polar water dissolves ionic compounds, and when it does, it looks like this. So it starts out with the positives and negatives attracted to each other and attached, and the water is then attracted, because it's polar, to the positive and negative ions. So the negative ion gets surrounded by the positive side of water. The positive ion gets surrounded by the negative side of water, and they all just get pulled apart until they're all in solution or dissolved. Draw these two pictures. The negative surrounded by the positive side of water, and the positive surrounded by the negative side of water. That's why like dissolves like. So in polar solutes and polar solvents, it's that pulling apart. With the nonpolar and nonpolar, it basically just kind of gets in between. That's how those get pulled apart. Okay, so then once this is dissolved, you have these separate ions, positive and negative, and that's why it can conduct electricity. Because conducting electricity is moving charge, and moving charges is what you need. So that's ionic. The next one is a special type of covalent. It's called covalent network. Covalent network is when group 14, carbon and silicon mostly, make covalent bonds with each other. These are special because they make 4 bonds. So carbon bonds to itself 4 times. Carbon to carbon, carbon to carbon, carbon to carbon, carbon to carbon, over and over and over again. This one, with this structure that's 3-dimensional, this is diamond. And it's that over and over and over structure that makes diamonds so strong. They're rigid, and they have high melting and boiling points. But the thing is, carbon again can make this, where it's just carbon to carbon to carbon to carbon, double bonded in sheets, that makes graphite. So both carbon, but very different forms of carbon. Diamond is hard and rigid and sparkly and crystal. Graphite is the stuff your pencil lead is made of. It's soft. It's in sheets. That's what makes it good for pencil lead. And it does conduct electricity because it's in those sheets, in that one plane. So those are just two examples of covalent network. Covalent network, they're always going to talk about carbon and silicon. That's going to be your clue, is that they're making bonds with each other. The next one is plain old molecular solids. This is just any other non-metal. These have low melting points, and they do not conduct electricity because they're usually London dispersion forces. There are not free charges here. They are held together, but these intermolecular forces aren't as strong. Low melting points do not conduct electricity. All right, the last one is metallic solids. These are metals to metals. The way this works, the way metal or metallic bonding happens, is we're talking about the big metals, like copper and iron and gold and silver. So they have a great big nucleus with lots of protons, and they also have a large electron cloud. The nucleus of this is attracted to the electron cloud of this, and this, and this, and they're all just attracted to each other, positive to negative. When this happens, you get all these electrons. We call that the sea of electrons. And that sea of electrons makes metals be able to conduct electricity in all states. Solid, liquid, gas, aqueous, they conduct electricity because of their electrons. In addition, these huge attractions from nucleus to other electron gives them high melting points. So high melting points, and they always conduct electricity. In addition, this sea of electrons is what makes metals malleable or able to be bent without breaking. It also makes them ductile, where we can stretch them into wires without them breaking. It's all about the sea of electrons in metallic bonding and metallic solids. Okay, the last thing I want to talk about today are alloys. So an alloy is a mixture of metals. There are two types of alloys. The first one is called interstitial. In case you can't see it, it's interstitial alloys. And this is when you have a large metal, like iron, with its metallic bonds. And a smaller element or a smaller atom comes in, and it gets in the empty spaces, like carbon in this case. Little tiny carbon stuffs itself in between the iron to make an interstitial alloy. This interstitial alloy is called steel. This is steel. The other type of alloy is called substitutional alloy. In substitutional alloys, you take one metal and you replace some of those metal atoms with another metal that's a similar size. So an example of this would be taking the coppers and replacing them with zinc. Not all of them, obviously, just some of them. But they have to be similar size, not the same, but close. When we mix copper and zinc and replace those in a substitutional alloy, we make brass. What's the point of an alloy? Why make an alloy? Yep.
To make element stronger.
To make the metal stronger. So metals, I just said, are malleable and ductile, meaning that they bend easily or they get dented easily. You don't want to make a bridge or a building out of a metal that bends easily. So they took iron and they replaced, or they stuffed some carbon in between to make it stronger, to make steel, so that our buildings and bridges don't bend. We want them to flex a little bit, but we don't want them to bend. Same thing with jewelry. Whenever you go to the jewelry store and you buy gold, you usually buy 16 or 18 karat gold. That's an alloy of pure gold, which is 24 karat gold. You would not want a ring or a necklace or a bracelet made out of pure 24 karat gold, or every time you hit it on something, it would get dented. We make alloys so that our jewelry is stronger and it lasts longer. So alloys are always less malleable and basically just stronger, more rigid. Got it? All right, let's do one example and we're done. Okay, so this is some substances A, B, and C. It gives us their melting point. Do they conduct electricity when solid? Do they conduct electricity when liquid? Substance A has a melting point of 400, does not conduct electricity when it's solid, but it does conduct electricity when it's liquid. What could it be? It's ionic. Ionic compounds have fairly high melting points. They do not conduct electricity whenever they're solid because those ions can't move, but once they're molten, they can. B, melting point of 2,000 degrees Celsius, conducts electricity when solid and liquid.
Metallics.
This is metallic. Metals have very high melting points, and they always conduct electricity. C, -6, never conducts electricity. This is molecular, plain old molecular.